just to mention that we reserve the seminar room at 1:30 for us to discuss the technicalities related to this work. So if you have a very specific question, you are invited to ask, but if it's too specific, probably it's better to postpone the discussion later today. But this is only because there are a lot of issues that will be, we already started to discuss and will be developed more during the session this afternoon at 1:30.
Okay. So thanks a lot, Stefano, for the introduction. And it's a pleasure for me of being here in Bologna to present for the first time, as Stefano already said, outside the eROSITA collaborations, the first cosmological constraint coming from the eROSITA All-Sky Survey. So as you can see from the title, the talk is about cosmology. So what is cosmology exactly? What is this talk going to be about? So there are many ways in which one can talk about cosmology. One can talk about how the universe evolved, how the content of the universe evolves. One can think about cosmological parameters, but I'm trying to stay away from equation as much as I can, unless I think it's necessary and useful for the discussions. And cosmology is truly what it's about is how. What? Okay, it's a bit squeezed compared to my screen for some reason. Let's. No, it's not. Okay. Okay, it's a matter of perspective. From my side, it was looking extremely squeezed, these images, so I was worried that something went wrong. So cosmology is about formation evolution of the universe, how we go from the initial very smooth initial state that we have from inflation, and how then from then we form stars, galaxies, galaxy clusters, and overall the large scale structure that we see in the universe. And in the recent years, thanks to Planck, we're able to have these exquisite first images of the universe that we observe at the CMB. So at like 300 and something thousand years after the Big Bang. And these images that, as you can see here, are widely exaggerated scales of the initial density field that is observed with the CMB. And the Planck team did a very exquisite analysis and were able to measure cosmological parameters with extreme precision, as you can see here on the left column, on the right column of the table that you see on the left. And so one can think about the fact that Planck actually enabled us to perform precision cosmology basically for the first time. However, is that the end of cosmology? Why do we want to do cosmology after Planck? That is a very good point that I think needs to be addressed at the beginning when one wants to do cosmological constraints. So we know that that's not the end of the story because, for instance, it's in the recent years, it has been shown from several different kind of probes that there are some tension in some cosmological measurements. For instance, the H0 tension is a very well-known tensions that when you measure the H0 from the CMB from Planck, you get a low value around 67 kilometers per second per megaparsec, while local measurement from distance ladder, for instance, tend to have a higher measurement of around 73 kilometers per second per megaparsec. And plus, you also have the so-called S8 tension. S8, as you can see here in the bottom label, is just a combination of omega matter and sigma 8, so two cosmological parameters. And basically, also in this case, it's less in tension compared to H0 tension, but still there is some tension in the sense the fact that the S8 parameter that is measured by the Planck CMB, which is basically represented by this vertical bar that you see here, it's kind of on the high-end side compared to what is measured from other experiments, which are color-coded by the so-called method, more or less. Like, more by the survey than the method, but okay. The point is the fact that you see that measurement from cosmic shear, that's 3 times point correlation function, Kidd shear, HSC shear tend to be on the lower end side here. And also from like PEO, you get also on the lower end side in some cases, but not all of them. And as the bottom rows represent the recent measurement on SPT clusters and SCR1 clusters, which are also on the low end side. So it looks like also in this case, there might be some potential tension with the lambda CDM model measured by Planck. And furthermore, it's true that the cosmological parameters are being measured with extreme precision by Planck, but some of them required a combination with external data sets. This is like an example for the two parameters like W, which is the dark energy equation state, the ratio between pressure and density of dark energy. And as you can see, the Planck contours alone are the blue contour here. So Planck alone by itself predicts, I mean, it's not really able to measure W very well, especially since W is like a late time, dark energy is a late time phenomenon, while Planck is mostly sensitive to the early parameters. And you see that only when you combine with like supernovae and BAO, then you're able to get this very explicit constraint that you get here in the center, and tell us that basically W is close to -1. And the same is also true for the curvature of the universe, omega k, and also in this case you see that Planck alone, it's on the lower end side, so it's slightly below 0 as reference value, and only when combined with external data sets like from supernovae from Pantheon or BAO from SDSS, then it's able to actually put some constraint there. So I hope I have slightly convinced you that there is something needed more than Planck, so it's not the end of the story. And the second thing that is an important topic of this talk is clusters. So why do we want to do cosmology with clusters? There are several ways to do cosmology, of course, but especially why do we want to do with clusters? So if you take, for instance, a patch of the image that I showed you before from Planck satellites, and you see the thing you see here are temperature fluctuations that are very small, 10 to the -5 in a relative error. And if you project along one direction and you imagine that in a, let's say, in a 1D instead of 2D, what you will see is the fact that you have some kind of uniform field with very small 10 to the -5 fluctuation, which here are widely exaggerated. And from time to time, you have some bigger fluctuations. Of course, the initial density fluctuations that are predicted by the inflation should be Gaussian. So you expect to have mostly, let's say, low fluctuation, but you also expect to have something in the tail of the Gaussian distribution. So from time to time, you have a big fluctuations. And if you put this kind of big fluctuation of this fluctuation overall in general, and you put them in some simulation, allow the simulations to evolve, you will see that when you reach the present time, so redshift 0, you will have that this initial fluctuation here, this is like one of the big fluctuations that you see, it's going to evolve and form like galaxy clusters, but also other groups, for instance, and overall form the large scale structure that is present today. And yeah, so clusters overall are able to actually trace. So when you detect cluster, you're actually detecting this highest density peak that you observe in the primordial density, in the density field. I mean, you're observing that nowadays evolved the peaks of the density field, but those will very well trace the primordial density field because clusters live on a quasi-linear scale of, evolution of the perturbation. So more or less you can approximate that clusters actually trace the peaks of the density fields. So by just doing some statistics on how many peaks you have, then you can actually put some cosmological constraints. And generally, this is visualized with the Halo mass function. So how many clusters basically you have as function of mass, but mass is basically a proxy for how peaked the initial field was as function of mass and distance, so redshift. But of course, mass is not exactly a direct observable. So generally, you also combine with some astrophysical probe because you measure, you count how many clusters you have as function of your physical observable and distance. And just to show you a small example of how that affects how cosmological, how clusters number counts is affected by cosmology and vice versa. I have here an example. You have the red to yellow curve at a low redshift, 0.1, and the other one at a higher redshift. And you see that when you change omega matter from 0.2 to 0.3, for instance, you see that the number of clusters you see changes kind of dramatically. But of course, it's not that easy because, okay, there are also degeneracy within cosmological parameters, so you can find different combinations that can also explain that, but let's ignore that for now. The point here is the fact that with clusters, by counting clusters, you are sensitive to cosmological parameters. The third element that was in my title was SRG eROSITA. So first of all, what is eROSITA? eROSITA is like an X-ray telescope that has imaging and spectral capabilities. Here you can see our actual image of eROSITA and an actual spectrum of eROSITA from the same image. And eROSITA is like an X-ray telescope which is orbiting the Earth and the Sun at L2 and in the L2 point. And it's comprised of around exactly seven telescopes that for those who are familiar with other X-ray telescopes, like XMM, for instance, the kind of detector that are present in each telescope are very similar to the PN detector that are present on XMM. It has a quite good, decent, let's say, spectral resolution and spatial resolution. But the real advantage that it has is the actual field of view. That is very large. But why exactly do we want to use eROSITA? There are many other telescopes around, and so why eROSITA? And also why especially do the detection with the X-ray emissions? So detecting cluster, you can do it in several different ways. You can detect them using the galaxies that you see in optical images. For instance, you see the example of COMET-DSS. But you know that galaxies in clusters form just 1 to 2% of the total mass of the systems. You can also use radio in principle, because you can have that relativistic electrons are accelerated around clusters, and then also produce some signal. Here, the example of COMA in LOFAR. But the amount of matter that is present in relativistic electron, you can see it's very small. And then you have the ICM, so very hot in the cluster medium, that is emitting in X-ray, but is also visible to as the effect. So, and those, the amount of baryons, the amount of matter that is in the ICM represent around 14 to 15% of the total matter in galaxy clusters. And the rest, which is not in the sum here, is the form of dark matter, which is not really visible by definition, but kind of. And the point is the fact that among the normal matter that is present in galaxy cluster, the largest amount is present in the intercluster medium, which is bright in X-ray. And so in our case, we have X-ray. We have X-ray detections. But why among the different X-ray detections? Why eROSITA? The reason is because if you look at an image for a cluster by channel, for instance, you see only a very small patch of the sky with some average exposure time. In XMM, you need more exposure time to cover a large field of view and also measure the properties of the cluster in the center, but also in the outer part. But in eROSITA, with a relatively short exposure time, we're also able to cover very well the clusters out to very large distances. So basically, having a large field imager in X-ray enables to perform a null sky survey. And in fact, eROSITA has been performing from basically December 2019 until June 2020, a null sky survey, and it also was doing that once every 6 months until the start of the Russia-Ukrainian war. And probably some of you have already seen these beautiful images that was released by the collaboration a couple of years ago regarding the images of the first null sky survey and what was observed. And then, of course, you run your detection tool and you detect clusters, and then from there you go ahead. But the point that here I want also to make is the fact that you need also to measure the redshift of this cluster, because the redshift measurement, without the redshift measurement of these clusters, you're not really sensitive enough to the Helio mass function, and so the constraint becomes quite weaker because you are just constrained dependent on the mass part, not on the redshift part. And so we are using the Legacy Survey DR10-South, which here on white, you see the footprint on the same physical scale in the previous images. And so you can see that the galactic plane is cut out from the Legacy Survey DR10, plus the Legacy Survey DR10 is not fully present in our sky. There are some patches that is missing other than the galactic plane. For instance, here you have the South ecliptic pole where the LMC is the small Magellanic cloud are present. And so it's not present in our analysis as well. And plus there is a small patch here where it's in the north of sky that is present in DR9. For the main catalog, we use it also the DR9 to fill up this gap here to the right-hand side. But for cosmology, we wanted to have something more uniform, so decided to stick with only one optical confirmation tools in order to have uniform richnesses and redshifts. And basically, the point is you have your X-ray images of clusters, and then just to summarize briefly what is the pipeline, to go from there to our example that we use for cosmology. So you start from the whole sky detection of clusters, and by sky I mean half sky. Sorry, I mean half sky in the German half of the sky. So on this plot, I mean everything to the right hand side of this line, and on the overall sky we detect a bit more than 900,000 sources, but the majority of them are regions. which we are not interested for the moment, for the cosmology, with clusters especially. And so we select only the ones that are extended, so the ones that are synchronously extended from the detection. And we found a bit less than 15,000. And then we do optical confirmation. And the optical confirmation is done with Legacy Survey DR10, as I mentioned, but also in the patches where Legacy Survey DR10 is not present, we also have DR9 there. And out of these 15,000 clusters, we are confirmed around 30,000 clusters. But then from that, we also select a cosmological sample by making a more secure cut in extended likelihood, because we wanted to have a lower contamination level in our sample. And also we selected only the clusters that were present in the Legacy Survey DR10 footprint, because we wanted to have uniform measurement on the redshift and the richness of the cluster. Plus, we also choose a redshift cut between 0.1 and 0.8, because I'm going to show you in a few slides that there are some issues below 0.1 and above 0.8 in the redshift measurement, in the photometric redshift measurements. And what we end up with is a sample of a bit more than 5,000 clusters, and the purity that we estimate, so how many clusters we have compared to the total number of clusters, is about 95%. So okay, so I can say now we can also visualize them on the sky. And these like a simple images that show you where this cluster that we are going to use, this is the only cluster used for cosmology, are on the sky. So you see there are the points that you see, I think you can see, are color-coded using the Viridis Python color map. We move to yellow, and they are color-coded by redshift. So you can see the redshift scale here on the top. And the size of the point, they are slightly different from point to point. That is just difference in the count rate of each cluster. So if a point is slightly bigger, then like it is quite small, this is a bit bigger, this is even bigger. So the bigger one has the count rate, just for visualization purposes. Then on the background, you also see this in black to white color map. You see the exposure level of eROS1 in the German half of the sky, so the part that is below this line here. And you also see that here is the South Ecliptic Pole, which is also the region that has the highest exposure in eROS1, but unfortunately is where the Large Magellanic Cloud is located. So it's very great for people that want to study Large Magellanic Cloud, for that want to study cluster. That is kind of a region that is almost not really too well accessible. And also plotted here, you also see the footprint of weak-lensing surveys from KIDS, DES, and HSC, which is in green the HSC, in red the KIDS, and in blue you see the DES footprints. And so just to give you some, and those of course are very valuable because they will give us information regarding the weak-lensing tangential shear, which is a direct proxy of the potential well, the gravitational potential well of galaxy clusters. So it's going to give us a very good mass proxy for this object, to calibrate our scaling relations. And just to give you some numbers regarding these other surveys, we have an overlap of a bit more than 4,000 degrees with the DES, and in this area we have a bit more than 2,000 clusters. And these are the number for KIDS and for HSC. So it's clear that DES is the actual source, is the most source of signal in our case from the weak-lensing calibration. And yeah, then you can say, then we're ready. Let's go ahead and show you the results. But first of all, I want to try to convince you that we have all the ingredients necessary to perform the cosmological analysis using eROSITA clusters. So we need to have detection of a large number of clusters. In our case, we have more than 5,000 clusters detected with eROSITA. We need to have almost uniform and large optical coverage with optical, and in our case, we have Legacy Survey DR10-South that enables to get basically redshift and richness for all of these systems. Then we need to have a good and well-calibrated selection function. On that, I'm going to spend a few words in the next slides. Then we need observables. We need the X-ray observable. We are going to use the X-ray count rate, which are NH corrected. So why NH corrected? So of course, some of us that are familiar with X-ray pointed images from channel XMM know that when you observe some point in the sky and you look at the exposure time that is there. There is some effect that is called vignetting that makes your effective exposure time decrease as function of distances from the center of your observations. And so generally people, what I've been always doing is I divide that by exposure time in order to remove that part of dependence from exposure. And the NH correction is also done for the same reason, but because NH, of course, over our small observation doesn't matter, changes really, changes really a small amount, but over the whole sky, like you can see in the previous image here, like here you see the exposure map in the bottom, you can see that the exposure time varies quite a bit, and also the NH, you can imagine it varies also quite a lot from point of the sky to other point of the sky. So we just removed the NH dependence by setting the absorption to 0. And also I'm going to spend also a few more words in the next slide regarding the fact that we have the weak-lensing survey that overlaps in our datasets, but then we also to calibrate how this weak-lensing survey actually enables us to measure the masses and how well they actually able to measure the masses of these objects. And more than measure the masses, I mean calibrate the scalar relation, but you get my point. And also we need also a good statistical tool to model our observable. I'm not going to go into any details again in that because that is a lot of equations and integrals that if someone wants to ask, maybe it's better to ask in the afternoon session. And then also, since we have contamination, we need some sort of way of removing or model our contamination. And I'm going to spend a few words on that in some of the next slide, but the point, but if you want to way more details on that, also in that case, ask a little bit later, but I think I'm going to explain that a bit well. So first of all, let's start from explaining what is the weak-lensing bias and how we deal with it and how that enters our equations. So first of all mass proxy are biased. There is not a single mass proxy that exists that are not biased. However, the factors that contribute to how biased our weak-lensing mass estimate is, we think they are under control and can be calibrated, especially using simulations. So just to make a simple short list of the biggest effect that contribute to the weak-lensing bias, I have a list here. So sphericality, because our clusters are not spherical, they have some elongation. They also can have some substructures, some subhalo, or some asymmetries in the distribution of the matter. You can use the wrong center, not exactly the dark matter center, in order to estimate the shear that is created by these clusters, and then you can have baryonic effect. But luckily, all of these effects can be well calibrated by simulation, and by that I mean the fact that we took basically we used the work that was done preliminary by Sebastian Grandis et al. In 2021, and the idea is we take a hydrodynamical simulation. We took magneticum and TNG. And from that, we get projected surface density map of clusters. So you get something like that for each cluster. And then from that, you can predict using the specific survey properties on the background sources that creates your lensing signal. You can get shear maps. But then, of course, when we get the shear profiles from our cluster, we don't care about the angular size, so you put that in only, you collapse this angular dimension there, and you get your shear profiles, you apply your statistical tool, you get some estimation of the weak-lensing mass, and what you get is something like that. It's also from Grandis 2021. For eROSITA, there will be updated plots, but more or less the point will always be the same. So you have your true masses from the simulations, and you have the masses you're recovering when you apply the properties of the survey on the simulations. So that will be different from DS, will be different with KITS and the HSC as well. So all of these plots will be different. But the point is the fact in all of the three cases, what we do is to basically fit a relation between the two. But not just that, we're also interested how these relations evolves with redshift. So we have the simulation at different redshift bins, and we need to interpolate between the bins. And also we need also to take into account the scatter, both intrinsic and the one caused by the fact that we're using simulation. Everything needs to be propagated into our analysis. And the end result that we end is like it is the mass dependent, but you also get the redshift dependent of the bias. And this is more or less what you get. I mean, this is exactly what you get in the case of DS. So you just focus on the line in the center here, the orange line. The orange line represents the average weak lensing bias in each redshift bin of the simulations, and is interpolated between the simulation redshift. You see linearly interpolated, and more or less you can say that they are on average we are around 7%. One thing I forgot to mention: this weak lensing is just the natural log of the ratio between the weak lensing mass and the true mass. So basically, log of that divided by that, and you see that higher ratio you have a little bit more bias. And one more point I wanted to focus in this pink contour and the brown contour. The pink contour is how much of the scatter that you see in this plot here was caused by differences from simulation to simulation, from mass bin to mass bin, from redshift bin to redshift bin. And the brown instead is the total systematic uncertainty, so includes also the fact I mentioned before. So the point here, the fact that at low redshift up to 0.4, 0.5, we are dominated by systematics coming from the hydrodynamical simulations. And at higher redshift, I remind you that in the cosmological sample, we stop at 0.8, where we have a simulation snapshot even a bit above, because we did interpolation of that 0.8. So at higher redshift, we start to get also dominated by the other source of systematics. And from this, what we need to pass on from the analysis is not just the mean, as I mentioned, but also the scatter around it. So which is very important to also put a full forward model. And then this is like after you get to some calibration of scaling relation, the thing is we need to go back and see whether we have calibrated the scaling relation well. So what we do is we first use this weak lensing information, we calibrate everything, we do the whole analysis, and we get some scaling relations calibrated, but then we need to say, are these scaling relations are calibrated good enough from our measurements? So what we did is choose, in this case, it is DSKs as well. We choose 25 bins. We've been encountered and been in redshift. And in each bin, what we did is take what is the predicted shear profiles from our clusters and stack them, take the measured shear profiles in DS and stack them. And the white points are the stacked measurement, while the purple curve is the stacked predicted shear. And one thing that is important here in the stacked prediction, we forget that we had a measurement of the tangential shear, so it's like a pure prediction of the weak length tangential shear from just the count rate and redshift of each cluster, basically. And the thing you can see from this plot is the fact that this is almost always a fit to the data, even though it's not actually a fit to the data. There are some cases where there are some deviation, like you see here, these bins where you have some 3 points that are above the line, but this is something that can statistically happen in one of these points. And also because if you look at the same redshift beam, you see that this is the only beam that has some issues. And you look at the same counted beam, it's also the only counted beam that has the same issue. So yeah, it can happen statistically. And overall, we computed the chi-square, even though we didn't fit again. And the overall reduced chi-square is about 1, a bit more than 1. So it's completely fine. And it shows that the magenta line, I call it purple, I think before, but okay. The magenta line is basically you take in each beam, you have calibrated your scaling relations. From your scaling relation, you predict again the weak lensing mass, and from the weak lensing mass, you predict again using the survey-specific properties, the tangential shear, and stack those in those beams. Because here, for instance, there are maybe 100 clusters, so you stack the signal from these 100 clusters and compare with the stack measurement of the tangential shear. So these are two independent way of, these are a way of checking that after you have done your weak lens, your whole analysis, then you are consistent with what was the tangential shear that was measured. So saying that this is just to say the fact that we are calibrated the scaling relations encountered and the mass correctly. I don't know if you explain that correctly.
And why don't you fit your data? Why don't you fit your data?
Because the fit of the tangential. So we first fit the tangential shear with the Wilkinson model, and then also take into account the covariance between Wilkinson mass and count rate. But then also we need to check whether we have calibrated correctly the count rate to mass spinning relation. So we forget we have the shear, and we say, given this count rate for this object, is the shear that you're going to predict using the whole formalization setup correct? And the answer is, the purple is what you get by not knowing you have measured the tangential shear, and the white point is what you have measured. So it's not a fit to the data, but it's what you can trace back from your analysis. Because in the forward model, you never pass to this kind of individual fit, but then at the end you can go back and see what was going to happen under the hood. Okay, so the other thing that I wanted to talk about was very briefly is the fact that our redshift uncertainty on the cluster distances are good in the redshift integral we have considered, so between 0.1 and 0.8, and by that I mean the fact that you follow the blue line. It's basically on the zero difference between the photometric and spectroscopic redshift for all the white points, which are the galaxy clusters, for which we also have spectroscopic measurements. So, and the scatter around it, which is represented by this dashed, not dashed. Yes, it's a dashed line, but it was the field region. The field region, it's also fully well within the one-to-one line. But if you look above redshift of 0.8, because above redshift 1.8 there is filter transition in the optical, you get worse estimation of your photometric measurement, and above 0.07, above 0.1, let's say, roughly, let's be conservative, you also get here that your redshift estimates are getting quite off. So those parts, low redshift and high redshift, we discarded from the sample, and in the rest of the sample, the overall photometric versus spectroscopic uncertainty are quite good. And if you compute, for instance, delta z over 1 plus z, you get that the average is around 0.5% on the 1 plus z measurements. And okay, then next point that we needed to address before going to the actual result is the selection function. So our selection function is based on simulations. Those work were basically published a couple of years ago, last year and 2 years ago, by Riccardo Seppi and Johan Compara. But basically, in summary, I'm not really an expert in that. The point is, we took dark matter only simulations from unit 1.1, and with a large 1 gigaparsec covariate box. And what we do is we populate the dark matter halo using a covariance matrix that was built to couple mass, redshift, and cluster profiles to the mass, temperature, and other observable that you observe for these clusters. In this case, we used high flux, XPL, XCOP, SPT to populate the dark matter halo. But of course, the sky is full of AGN, as you know. So we also populated the AGNs using the Lagrange gas distribution from previous observations. We also populate the universe with stars, but mainly stars are on the Milky Way plane, but the Milky Way plane, it's not in our footprint, so I don't really talk about how we simulate also stars. And then everything is fed to Sixter, which is a simulator, photon-based simulator of actual observation of X-ray skies. And then we actually do the actual pipeline. So you have your input sources, you have your detection chain at the end, and then you can do an association between what was simulated and what was detected. And you can basically do that in, let's say, beams in mass and redshift, and you say this beam of mass and redshift, how many of them have I simulated, how many of them do I detect? And then you have some detection probability that you can estimate. Of course, this is a very simplified version. In reality, we use the Gaussian process that is a pseudo machine learning way of training everything on 2/3 of the sample and testing that on the rest of the sample. Everything we're going to be described more detailed in Clark et al. Paper. And the only thing we need from that is the actual selection function. And the selection function is just an example of what we get out of it. So it's the probability of including a cluster that has some properties like count rate, redshift, and also with this HI, I mean sky position properties that include NH, background, exposure time. And one thing I wanted to focus slightly now is on this first row here, which shows what is the probability of detecting a cluster given count rate and something else, basically. And the thing you notice is in all except this row here, the isocontour that you see here that represent isoprobabilities, they are almost vertical, which means that a small shift in count rate will go very fast through the isocontours of probabilities, which means you make a lot of difference in the detection, in the probability of detection of a cluster, while a shift in either redshift, background of eROSITA or NH at that sky position does a really small impact on the detection probability because you're going vertically in those cases. And again, especially on NH, this is because this count rate is not exactly count rate, it's count rate which has already been NH corrected. So part of the fact that was so when you correct by counter, you see that there is almost no residual dependence on the NH in the selection function. Exposure time is a little bit different because, of course, the deeper you are, the earlier the transition between non-detection and detection of clusters happens. And the other thing is regarding the sky properties, which you see in this horizontal part here. If you focus on the exposure time versus something else, we already talked about this, but you see that in the case of exposure time versus NH, a change in NH, so going horizontally here, doesn't really change that much the contour level in probability where you are, while going vertically, it has a much bigger impact, and the same is true for background and redshift. So the point here is the fact that although the selection function we use depends on count rate, redshift, NH, background, and exposure time, the major contribution there are mainly from count rate and exposure time. Okay. And then contamination. So just a quick calculation. We have detected 5,200 clusters, more or less. If you naively assume those follow up some statistics, then you can say, what is the Poisson noise on this data? The Poisson noise on this data is square root of n over n. So you get around 1.4, 1.5%. I mentioned you before that the purity that we expect to have was 95%, which means that you complete that to 100, you get 5% that is expected contaminations. So in our case, contamination is above the Poisson noise, which means that in principle, contamination, even though it's at only at 5%, is affected our sample and needs to be addressed somehow. So how do we do that? So let's say you have a sample of clusters. Of course, you can see they are not clusters, but are fish. And let's say that you have your contaminants there. So the question is, these are the things you want to see, but these are your contaminants. How would you go and tell to someone that how to find the contaminant? So you see that these other fish has a different color. These are black and yellow. These are red. So it has a different color. You also see that all of them are swimming simultaneously to your right-hand side, while this is swimming toward you. So it's going in different directions. And also you can see that the shape of the overall fish is kind of triangular. This is different. So overall, you can conclude that you can distinguish this contamination because it has different properties in your observable space. So you can say, yeah. And the same is probably also true for clusters. So we need to do that. We try to look for if there is a region in the parameter space for some particular combinations where you can actually say this is a cluster, this is not a cluster, for instance. And the idea, and we find that when you plot richness versus count rate in redshift bins. And the thing you can more or less see by eye, but I will guide you with some lines that are drawn by hand, is the fact that if you look closely there, you will see that there are some part of the population that in the count rate versus richness that follow more or less scaling between one and the other, which is what you expect from a cluster. You expect that cluster that has a higher richness should also have a higher count rate, while you don't expect that behavior for a contaminant. And that's actually what you start to merge in the lower part here on systems that have a low count rate and a low richness, let's say. And so there you find your observable. So in this parameter space, in count rate versus richness versus redshift, we found, at least for now, a visual way of identifying the contaminants. And then, of course, we need to build a statistical model that is able to actually forward model everything here. And the idea is very simple. It's based on what is called a mixture model. A mixture model is when you have two populations or more population that comprise your sample. And your overall statistical distribution looks like the red one, for instance, in a simple case like this. And so in this case, you need to model where the P0 population is, where the P1 population is, but also what is the relative fraction of population 0, population 1 is. Yes?
The red map, the richness, which richness is it?
So the richness here is the richness from what we call eROMapper, which is basically a sort of pointed red mapper.
The red map.
Yeah. And so coming back to what I wanted to say, you have two populations. You have to model where they are in the parameter space and how many they are. And the weights in which you add the two up, they are not completely free because you need overall to have the integral of your probability distribution function to integrate to one. So if one has some weight of f, the other one has weight of 1 minus f, of course. So for each subpopulation we have an extra nuisance parameter that we want to fit plus where the population is. And this is like an actual example of what we find in our catalog, because I told you some previous slide that in the overall catalog there is almost 1 million AGN. So, but some of these AGN also leak into the cluster catalog, and this is also what we expect from running our red mapper, eROMapper on the AGN catalog. But also some background fluctuations, so you can have your X-ray background that is, of course, not perfectly uniform. Sometimes you can have some variation that can be detected as clusters. So overall, we also need to model a second population of contaminants. So overall, two populations of contaminants, AGN, but also randoms. What?
5 million.
Oh, okay. Okay. And then we also have the cluster population and overall they sum up to form the overall model that we have. So I didn't show any questions here, but if you want to ask for a question for that, ask later. So, okay, let's go to a slide of result in 5 minutes, if I can. So these are the first result on the lambda, on the omega matter versus sigma 8 case. And here I show only compare with other cluster probes, plus Planck CMB, of course, and also WMAP. And the orange one are our results, our main result for eROSITA run alone. And you see that compared to other clusters, we have on the upper right-hand side, except XXL, which is the purple curve that you see here. And plus, we are also consistent with the Planck CMB, and also we did a combination with Planck CMB, and it's our result. If you want also another combination with different kind of probes, which are not clusters, you can see here the combination with Planck lensing, with ACT lensing plus DEO, and also you have like DES 3 times 2 Planck correlation function and DES plus kits analysis. So compared to these kind of other probes, we are okay. We are in agreement with some, but not with others, especially the one with that had this cosmic shear experiment included, like DES plus kits or DES 3 times 2 Planck correlation function were a bit on the higher end. And that actually, oh, and those are the parameters if you want to look at them. But this is actually what I wanted to talk a bit more about. So the S8 tangent that I was talking at the beginning, this is the first point is where we stand. The second point is where we are when you come down with Planck. So compare with let's say SPT clusters, we are on the we are consistent with Planck, but on the let's say on the other side of the things, consistent with excelling in practice, and instead compare with other cosmic shear correlation function, we still have some tangent. So since I don't have time, I need to move forward. So to result regarding neutrinos. So one thing I want to focus to put your attention on one moment here is the fact that with cluster you're able to put constraint on neutrinos, which to me it's mind-blowing because clusters are among the biggest massive objects you find in the universe, and neutrinos are the biggest non-zero mass objects that are present in the universe. So it's very remarkable that the two are connected. And just to show you how the neutrinos affect the mass function, you show the neutrino damp structure formation. So you see that as you increase the sum of neutrino masses, you basically dump your number of halos. And there is also a key point that is the fact that neutrinos have masses. We know that since the end of the 90s, thanks to oscillation from the sun, neutrino oscillation experiment from the sun, and we have, but we are not sure about what is the correct model on the neutrino masses. There are two most dominant competitors here, the so-called normal hierarchy model and inverted hierarchy model. the key point only coming from here that is need to put forward the fact that the lower bound that the two different model gives us, depending on the same experiment from oscillation, are slightly different. One is like 0.059 electron volt, the other one is 0.101 electron volt. And also we have upper limits on these kind of neutrino masses from other direct experiments, from like tritium decay or beta decay, but more or less the range is below 1 electron volt. Plus we also have a tons of indirect experiments, mainly based upon the Planck CMB results. And the general result is a bit tighter than direct experiment, but mostly due because we have fixed the so-called framework in the nuwCDM. And there are a lot of work that also go into more details regarding this. And this is what we obtained with eROSITA, always orange color to look at. And green one is what was previously obtained by SPT, and blue one is what is obtained by Planck alone. So as you can see, if you look vertically, in vertical direction, we're basically almost at basically the same level as Planck. And in red, you also see a combination with Planck. And final table with numbers, maybe too little alpha here, but the point is we alone, we get an upper limit at 95% confidence levels of 0.22. When you combine with Planck CMB, we get an upper limit of 0.11, which is extremely remarkably close to the value that is almost excluding the inverted hierarchy model, which is 0.0101. So we are getting almost at the level where the inverted model is almost not allowed anymore. But then if they say, okay, this result does not really depend on what is the neutrino mass model, I mean, a hierarchy model that is used. So then we can couple with one or the other. And when you bound from below and above, then you don't get anymore an upper or lower bound, you get an actual measurement. So in both cases, you get, in those cases, you get this kind of mass for neutrinos for the normal hierarchy model and this mass for the inverted model. And one interesting thing here is, although basically, there is a relation that connects the lightest neutrino eigenstate, we can be M1 in the normal and M3 in the inverted one, that connects basically the mass of the lightest and the total mass. And the result, and which are the relation that you see here are solid lines, and the dashed line and the contours around it are our constraint in the, our constraint plus Planck and the lower bound from normal or inverted model. And this interesting thing that you see that if you naively intersect where our constraints and this model lie and go down, and do the same for the 16th percentile or the 41st percentile of our distribution, for both models, we more or less get the same mass of the lightest element, lightest neutrino eigenstates, which is, okay, it's M1 or M3. So that's quite interesting that even though this has a large error bar, more or less the order of magnitude is kind of that one, I think. And lastly, I want also to mention regarding our results on the wCDM cosmology, which is basically we allow the Arcangelo state W to be free, so pressure divided by rho free. And these are basically our constraint, is the orange control that you see here. And other thing that you see in this plot is the blue is the Planck alone, from CMB. You have in this brown here is the Pantheon plus result, and the green one is the result from SDSS-BAO, and this one is the Destro times 2 correlation function. And in this case, we decided to combine with Pantheon supernovae because it was quite already orthogonal to our result, so it's good to combine. And also Planck is also a bit far away by its own, and that is what we get. But also we use also some combination with Planck, and these are our results. So alone we get roughly 10% uncertainty on W. When you combine with Pantheon plus, we get roughly 5% uncertainty on W. And when you also combine with Planck CMB, we also get an even smaller uncertainty on W of 3%. So few slides less. Few slides. I think I'm already 10 minutes late, but some of you might forgive you. So we have also fitted the new wCDM cosmological model, where we also allowed both nu and W, some of neutrino masses and the Arcangelo state to be free. And this is important to show that the overall constraints on omega matter and sigma 8 do not really depend if you allow the extra parameters to be free. And the other interesting exercise is since in Planck CMB, they didn't put some neutrino masses to 0 as we did, but they froze them to 0.006. We also run that test and see whether that affects our result. Basically, they don't really affect our results. Then we have applied several several criteria to our samples. So, for instance, we have, if we cut at a higher extent likelihood, the contours don't basically move much. And also, if you remove the ratio between 0.6 and 0.8 and consider only the one between 0.1 and 0.6, then you get the green one, which also slightly slower on again, but overall, we're always consistent between the 68 percentiles. And also talk a little bit about this very nice mixture model, but overall, if we didn't do it, we'll still be in the same place, which is okay, comforting and also disappointing for all the effort we put in this mixture model at the same time. And the interesting thing is the fact that one important systematic that we have is regarding the choice of the Halo mass function, because we adapted in all our analysis the Tinker 2000 mass function, but we have used a different mass function. Our result might have changed some around one sigma, let's say in a set, E sigma 8. And so, yeah. And there are other cosmological papers that are going to come out at the beginning of next year, end of this year maybe. So regarding cluster clustering, regarding doing the power spectrum of whole sky, and also doing something in modified gravity. Here in particular, we did f of r gravity and changing the evolution of the growth factor. So for those who know, the growth factor is omega matter to the gamma, and gamma is 0.55 in the lambda CDM. Here we allow this gamma to be free, and we look what happens. And also we're going to put constraints on the action line dark matter using some action camp model. And this is going to be done by the person you see in the parentheses. And these are my conclusions. I think I went very fast in the result part. So let's go for questions.